Tonight, we're going to go deeper into matter than you've ever gone before. Past the atom, past the nucleus, down to the smallest building blocks of reality itself. Quarks. You've probably heard the name, but here's what almost nobody tells you. A quark has never been seen alone. Not once in the history of the universe. And this isn't because our technology isn't powerful enough. It's because the universe literally won't allow it. When you try to pull a quark away from its partners, something extraordinary happens. The harder you pull, the stronger the force resists. And if you pull hard enough, the universe would rather create entirely new matter out of pure energy than let a single quark exist by itself. By the end of tonight, you're going to understand why. Before we get started, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, make yourself comfortable and let's begin. Let's start with something you already know. Matter. The stuff you're made of. The stuff the earth is made of. The stuff your coffee mug, your phone, the air you're breathing right now is made of. Everything you can touch, taste, see, or smell is matter. And for most of human history, that's about all we knew. Matter existed. It came in different forms. Some of it was hard, some soft, some heavy, some light. But nobody knew what it was actually made of at the deepest level. Nobody knew what would happen if you kept looking closer and closer, peeling back layer after layer. The answer, as it turned out, would take over 2,000 years to uncover. And what we found at the bottom is stranger than anyone could have imagined. The ancient Greeks were the first to ask this question seriously. Around 400 BCE, a philosopher named Democritus proposed something radical. He suggested that if you took any piece of matter and kept cutting it in half, again and again and again, you'd eventually reach a point where you couldn't cut it anymore. You'd arrive at the smallest possible piece. He called these pieces atomos, meaning uncuttable. It was a brilliant idea, and it turned out to be partially right. But Democritus had no way to test it. He had no microscopes, no experiments, no technology to peer inside matter. So for over 2,000 years, the idea just sat there. A philosophical curiosity with no proof behind it. Generations of humans lived and died without knowing whether the material world was truly made of tiny, indivisible pieces, or whether matter was continuous, smooth all the way down with no smallest unit. It wasn't until the early 1800s that scientists started finding real evidence for atoms. John Dalton, an English chemist, proposed his atomic theory in 1803. He showed that chemical reactions could be explained if you assumed matter was made of tiny, indivisible particles. Each element had its own type of atom, and atoms combined in specific ratios to form compounds. It was elegant. It was testable. And experiment after experiment confirmed it. When hydrogen combined with oxygen to form water, it always combined in the same ratio. 2 hydrogen atoms for every 1 oxygen atom. This consistency made perfect sense if atoms were real. Discrete objects combining in fixed proportions. By the late 1800s, atoms were accepted as real. Scientists could measure their approximate sizes. They knew that a single atom was incredibly small, roughly 1/10 billionth of a meter across. If you lined up about 1 million atoms side by side, they'd barely stretch across the width of a human hair. A single drop of water contains roughly 1 billion trillion water molecules, and each molecule is made of 3 atoms. Atoms were unimaginably tiny, and they seemed to be the fundamental building blocks of everything. The uncuttable pieces that Democritus had imagined over 2,000 years ago, millennia earlier. But then something happened that shattered this picture entirely. In 1897, a British physicist named J.J. Thomson was experimenting with cathode rays, beams of particles produced inside glass tubes with the air pumped out. He discovered that these rays were made of tiny particles much smaller than any atom. These particles carried a negative electric charge, and they seemed to come from inside atoms. They could be extracted from many different types of atoms, suggesting they were a universal component of all matter. Thomson had discovered the electron, and in doing so, he'd shown that atoms weren't uncuttable after all. They had internal structure. There were smaller things inside them. This was a revolution. For over 2,000 years, atoms were supposed to be the bottom layer of reality, the smallest possible pieces. And now Thomson had shown that atoms contained even smaller particles. If atoms had electrons inside them, what else was in there? What held the atom together? Thomson proposed a model where atoms were like plum puddings. A blob of positive charge with electrons embedded in it, like raisins in a pudding. It was a reasonable guess given what was known at the time, but it turned out to be completely wrong. In 1911, Ernest Rutherford designed one of the most important experiments in the history of science. He and his colleagues Hans Geiger and Ernest Marsden fired tiny, positively charged particles called alpha particles at a thin sheet of gold foil. If Thomson's plum pudding model was correct, the alpha particles should have passed straight through with only slight deflections. The positive charge was supposed to be spread evenly throughout the atom, too diffuse to cause major deflections. The alpha particles should have sailed through like bullets through fog. Most of the alpha particles did pass straight through, but some of them bounced back at extreme angles. A few even bounced almost directly, backward toward the source. Rutherford later said this was as surprising as firing an artillery shell at tissue paper and having it bounce back at you. Something inside those gold atoms was dense, massive, and concentrated in a very small space. Something was lurking in there that could stop an alpha particle dead in its tracks and send it flying backward. The implications were staggering. Rutherford concluded that the atom's positive charge and most of its mass were concentrated in an incredibly tiny core, which he called the nucleus. The vast majority of the atom was empty. Completely, utterly empty. The solid matter you feel when you press your hand against a table isn't actually solid at all. It's overwhelmingly empty space. What you feel as solidity is really the electromagnetic force between the electrons in your hand and the electrons in the table repelling each other. If you could somehow remove all the empty space from all the atoms in every human being on Earth, the remaining matter would fit inside a sugar cube. That's how empty atoms are. The atom was mostly empty space. The electrons orbited far from the central nucleus, like planets orbiting a distant sun. If you scaled an atom up to the size of a football stadium, the nucleus would be about the size of a small marble sitting at the center of the field. Everything else, the entire vast volume of the atom, would be empty space. That's how small the nucleus is compared to the atom. And yet, the nucleus contains over 99.9% of the atom's total mass. Almost everything that gives matter its weight, its heft, its substance, is concentrated in that tiny central point. This raised an obvious question. What was the nucleus made of? Rutherford suspected it contained positively charged particles to balance the negative charge of the electrons. In 1919, He confirmed this by performing experiments that effectively knocked particles out of atomic nuclei. He called these positively charged particles protons. A hydrogen atom, the simplest atom, had one proton in its nucleus and one electron orbiting it. Helium had 2 protons. Carbon had 6. Gold had 79. The number of the protons determined what element an atom was. Change the number of protons in a nucleus and you change the element itself. Turn lead into gold by removing 3 protons, at least in principle. But there was a problem. Helium had 2 protons, so it should have had roughly twice the mass of hydrogen. But it actually had about 4 times the mass. Something else was in the nucleus besides protons. Something with mass but no electric charge. Something invisible to electromagnetic measurements, but very real in its contribution to the atom's weight. In 1932, James Chadwick discovered the neutron, an electrically neutral particle with almost the same mass as a proton. Neutrons sit in the nucleus alongside protons, and they help hold the nucleus together. Without neutrons, the positively charged protons would repel each other through electromagnetic force, and the nucleus would fly apart. Neutrons act as a kind of nuclear glue, providing stability to the atomic core. So by the early 1930s, the picture of the atom seemed complete. Atoms were made of 3 types of particles. Protons, which were positive and sat in the nucleus. Neutrons, which were neutral and sat in the nucleus alongside protons. And electrons, which were negative and orbited the nucleus in a cloud of probability described by quantum mechanics. 3 particles. That was all you needed to build every atom, every element on the periodic table, from hydrogen with its single proton to uranium with its 92 protons and beyond, was just different combinations of these 3 building blocks. 1 proton made hydrogen, 8 protons, 8 neutrons, and 8 electrons made oxygen. 26 protons, 30 neutrons, and 26 electrons made iron. The entire material world, from the water you drink to the iron in your blood to the gold in a wedding ring, was assembled from just 3 types of particles. 3. The same 3 particles that made up a rock also made up a rosebud, a raindrop, a human brain. The staggering diversity of the material world, every texture, every substance, every color and form, all of it emerged from different arrangements of just protons, neutrons, and electrons. It was perhaps the most beautiful simplification in the history of science. This was satisfying, it was clean, it was elegant, and it lasted for about 20 years before physicists started finding serious problems. The first problem was that protons and neutrons didn't behave the way truly fundamental particles should. They seemed to have internal structure. When physicists smashed them together at high energies in particle accelerators, they didn't behave like solid, indivisible objects. They behaved more like bags of smaller things. The scattering patterns showed lumpy internal structure, as if something was rattling around inside. If protons were truly fundamental, truly point-like, the scattering experiments should have produced smooth, predictable results. Instead, the results were messy, showing hard, point-like objects inside the proton that could be individually struck by incoming particles. These experiments, called deep inelastic scattering experiments, were performed at the Stanford Linear Accelerator Center in the late 1960s. They fired high-energy electrons at protons and watched how the electrons bounced off. The electrons scattered in ways that only made sense if they were hitting small, hard objects inside the proton, not a smooth, uniform blob of matter. The physicists conducting these experiments, Jerome Friedman, Henry Kendall, and Richard Taylor, won the Nobel Prize for their work. The second problem was the zoo of new particles that kept showing up. In the 1940s, 50s, and 60s, particle physicists built increasingly powerful accelerators, and every time they cranked up the energy, new particles appeared. Pions, kaons, sigma particles, Xi particles, lambda particles, omega particles, dozens and dozens of previously unknown particles, all interacting through the strong nuclear force. It was chaos. There was no organizing principle, no periodic table for these particles. Physicists joked about needing a Nobel Prize just for not discovering a new particle that year. The particle zoo, as it came to be known, was embarrassingly messy. Nature was supposed to be elegant at its core. This wasn't elegant. This was a junk drawer. Something had to give. Either nature was absurdly complicated, with hundreds of truly fundamental particles and no deeper logic, or there was a deeper layer. Something simpler underneath all this complexity. Just as atoms had simplified the thousands of known chemical compounds into combinations of about 90 elements. In 1964, two physicists independently proposed a solution. Murray Gell-Mann at Caltech and George Zweig at CERN both suggested that protons, neutrons, and all those other strange particles weren't fundamental at all. They were made of even smaller particles. Before this proposal, Gell-Mann had already made progress organizing the particle zoo. He'd developed a classification scheme called the Eightfold Way, which grouped particles according to their properties into geometric patterns. It was like a periodic table for subatomic particles. But the Eightfold Way was descriptive. It organized particles into patterns, but it didn't explain why those patterns existed. The Quark model provided that explanation. The patterns existed because all those particles were built from smaller components. Gell-Mann called these components quarks, borrowing the word from a line in James Joyce's novel Finnegan's Wake. The line reads, 3 quarks for muster mark. Zweig called them aces, but Gell-Mann's name stuck. The word quark entered the vocabulary of physics permanently. The original proposal included 3 types of quarks, which physicists call flavors: the up quark, the down quark, and the strange quark. Each one had a fractional electric charge, which was radical because until that point, every known charge in nature came in whole numbers. The electron had a charge of -1, the proton had a charge of +1, but quarks broke this rule. The up quark carried a charge of +2/3, the down quark carried a charge of -1/3. The strange quark, like the down quark, also carried a charge of -1/3, but was considerably heavier. Here's where it gets elegant. A proton is made of 2 up quarks and 1 down quark. If you add up the charges, you get 2/3 plus 2/3 minus 1/3, which equals +1. Exactly the charge of a proton. A neutron is made of 1 up quark and 2 down quarks. The charges add up to 2/3 minus 1/3 minus 1/3, which equals 0. Exactly neutral. Just like that, the Quark model explained why protons had a charge of +1 and neutrons had 0 charge. It wasn't arbitrary. It wasn't a coincidence. It was a direct, inevitable consequence of the quarks inside them. But the Quark model did something even more impressive. It explained the entire zoo of particles that had been discovered over the previous 2 decades. All those pions, kaons, sigma particles, and others could be understood as different combinations of quarks. Some were made of 3 quarks, like protons and neutrons. Physicists call these baryons, from the Greek word for heavy. Others were made of 1 quark and 1 antiquark. These are called mesons. Antiquarks are the antimatter partners of quarks. Every quark has a corresponding antiquark with the same mass, but opposite charge. An anti-up quark has a charge of negative 2/3. An anti-down quark has a charge of positive 1/3. A positive pion, for example, is made of an up quark and an anti-down quark. Its charge adds up to 2/3 plus 1/3, which equals positive 1. The hundreds of mysterious particles weren't hundreds of fundamental building blocks. They were hundreds of different combinations of just a few types of quarks. It was like discovering that the thousands of words in a language are all built from an alphabet of just a few letters. The complexity was real, but the underlying simplicity was profound. Order had emerged from chaos. Over the following decades, 3 more quark flavors were discovered, bringing the total to 6. In 1974, the charm quark was found simultaneously by teams at Stanford and Brookhaven, led by Burton Richter and Samuel Ting, respectively. Both teams discovered the same particle, a meson called the J/PSI, made of a charm quark and an anti-charm quark. This discovery was so dramatic and so important that it's known as the November Revolution in Particle Physics. Both Richter and Ting shared the Nobel Prize. The charm quark has a charge of positive 2/3, like the up quark, but it's much heavier, about 1.3 times the mass of a proton. Then, in 1977, a team at Fermilab led by Leon Lederman discovered the bottom quark, sometimes called the beauty quark. It carries a charge of negative 1/3 and is much heavier than the strange quark, roughly 4.5 times the mass of a proton. Finally, in 1995, also at Fermilab, the top quark was discovered. The top quark is a monster. It carries a charge of positive 2/3, but its mass is staggering. A single top quark has roughly the same mass as an entire atom of gold, about 180 times heavier than a proton. The top quark is the heaviest known fundamental particle in the universe. It's so heavy that it actually weighs more than some entire atoms. And yet, it's a point particle with no known size or internal structure. All that mass packed into something with no measurable dimensions. It's one of the strangest facts in all of physics. The top quark is also incredibly unstable. It decays in roughly 5 times 10 to the negative in 25 seconds. That's so fast that it actually decays before it has time to form a bound state with other quarks. It's the only quark that effectively exists momentarily outside a hadron, but only for an inconceivably brief instant before it transforms into other particles. So here's the complete picture. 6 quarks arranged in 3 pairs, which physicists call generations. Up and down form the first generation. These are the light ones, and they make up all ordinary, stable matter. Everything you see around you, every atom in your body, every star in the sky, every planet, every grain of sand on every beach is built from up and down quarks and nothing else. The up quark has a mass of only about 2.2 million electron volts, and the down quark about 4.7 million electron volts. These are incredibly light, much lighter than a proton, which is about 938 million electron volts. This discrepancy between the mass of the quarks and the mass of the proton they make up is itself one of the deepest puzzles in physics. and we'll come back to it later because the answer is extraordinary. Charm and Strange form the second generation. They're heavier and show up in exotic particles produced in high-energy collisions or cosmic ray interactions. Top and bottom form the third generation. They're the heaviest and most unstable, appearing only briefly in the most violent particle collisions. These 6 quarks, along with their 6 antiquark partners, are sufficient to build every hadron, every baryon, every meson that has ever been observed in any experiment anywhere. Every single one. Now, let's talk about what quarks actually are in terms of their fundamental properties, because this matters deeply for understanding what comes next. Quarks are fermions, which means they have half-integer spin and obey the Pauli exclusion principle. No 2 identical fermions can occupy the same quantum state at the same time. This is the same rule that governs electrons and explains why the periodic table has the structure it does. It's why atoms have electron shells, why chemistry works, why matter has the properties it does. Each quark has several intrinsic properties. It has mass, it has electric charge, which we've already discussed, it has spin, an intrinsic form of angular momentum. For quarks, the spin quantum number is 1/2, and each quark has one more property, a property that turns out to be the most important one for our story tonight, a property called color charge. Now, I need to be very clear about something. Color charge has absolutely nothing to do with actual color. Quarks are far too small to have any color in the visual sense. They don't absorb or reflect light at particular wavelengths. Color is just a label that physicists use because the mathematics of how quarks interact has a structure that can be described using 3 types of charge, and they needed names for those 3 types. They chose red, green, and blue because these 3 colors of light combine to make white light. And this analogy happens to work beautifully with how the charges combine. They could have called them type A, type B, and type C. They could have called them any 3 names at all. The names are arbitrary, but the underlying physics is absolutely not. Every quark carries one of 3 color charges: red, green, or blue. Every antiquark carries one of 3 anti-color charges: anti-red, which you can think of as cyan, anti-green, which corresponds to magenta, and anti-blue, which corresponds to yellow. And there's a rule, a strict, absolute, unbreakable rule of nature. All observable particles must be color neutral. This means the color charges must cancel out completely. In a baryon like a proton, you need 1 red quark, 1 green quark, and 1 blue quark. Red plus green plus blue equals white, which is color neutral. In a meson, you need a quark of some color and an antiquark of the corresponding anticolor. Red plus anti-red equals neutral. Green plus anti-green equals neutral. This color neutrality requirement is why quarks always appear in groups, never alone. A single quark would carry an unbalanced color charge, and that's forbidden. The universe does not allow colored objects to exist as free, observable particles. But I'm getting ahead of myself. The color charge is what connects quarks to the force that binds them together. And that force, the strong nuclear force, is unlike anything else in the universe. It doesn't just hold quarks together, it imprisons them. And the nature of that imprisonment is one of the most extraordinary and counterintuitive phenomena in all of physics. Before we explore that force, let's pause and appreciate where we are. We've peeled back 4 layers of reality. We started with matter, the stuff of everyday experience. We found that matter is made of atoms. We found that atoms contain a nucleus surrounded by electrons. We found that the nucleus contains protons and neutrons. And we found that protons and neutrons are made of quarks. Each discovery took decades of painstaking experimental work and profound theoretical insight. Each layer revealed a world more strange and more beautiful than the last. Quarks are, as far as we know, the bottom of the ladder. They have no known internal structure. No experiment has ever found any evidence that quarks are made of something smaller. When we probe quarks at the highest energies our accelerators can reach, energies that let us examine distances less than 1/1000th of a meter, they still behave as point-like particles, objects with no measurable size or substructure. For all practical purposes, quarks are truly fundamental. They are the base layer, the irreducible letters of the alphabet from which all matter is written. But unlike letters in an alphabet, quarks cannot exist on their own. You will never find a lone quark sitting by itself anywhere in the universe. The reason isn't technological. It isn't a matter of building better equipment or more powerful accelerators. It's that the laws of physics forbid it. The universe has a rule, a deep structural rule built into the very fabric of reality itself, that says quarks must always be bound together with other quarks or antiquarks in color-neutral combinations. This isn't a limitation that some future breakthrough might overcome. It's as fundamental as the conservation of energy, as unbreakable as the speed of light. The universe simply does not permit a free quark to exist. This is profoundly strange. Think about what that means. Imagine building blocks that can be used to construct anything, but the blocks themselves can never exist independently. You could build houses, cars, bridges, anything you wanted from these blocks, but the moment you tried to hold a single block by itself, it would be impossible. The universe would intervene and prevent it. Not through some barrier you could theoretically overcome with better tools. Not through some force you could fight against with enough energy, but through a fundamental law of nature as absolute and non-negotiable as the impossibility of traveling faster than light. That's what quarks are like. They are the building blocks of all visible matter in the universe. Every proton in every atom in your body contains quarks. Every neutron in every nucleus of every atom, of every star in every galaxy in the observable universe contains quarks. Quarks are everywhere. They are among the most abundant things in existence, and yet not a single one of them has ever been observed in isolation. Not once, not anywhere, not in any experiment ever conducted in the history of science. Think about how unusual this is by considering other fundamental particles. Electrons can exist on their own. You can isolate a single electron, trap it in a magnetic field, and study it for as long as you like. In fact, physicists do this routinely. Electron beams are used in old television screens, in electron microscopes, in medical equipment. Electrons flow freely through metal wires every time you flip a light switch. An electron doesn't need a partner. It's perfectly happy on its own. Photons, the particles of light, also exist freely. Every time you turn on a lamp, trillions of photons stream into the room. Each one is an independent particle traveling at the speed of light. Photons don't need to be bound to anything. Even neutrinos, those ghostly particles that barely interact with anything, travel alone across the entire universe, passing through planets and stars without stopping. But quarks are different. Quarks are the great exception. Among all the fundamental particles we know of, quarks are unique in their inability to exist independently. They are permanently, fundamentally, inescapably bound to other quarks. And the reason is not that we lack the technology to free them. It's that freeing them is forbidden by the deepest laws of physics. Understanding why requires us to understand the force that binds quarks together. A force so powerful, so strange, and so fundamentally different from every other force in nature that it overturns everything you think you know about how forces work. A force that gets stronger, not weaker, when you try to pull things apart. A force whose carrier particles are themselves subject to the very force they carry, creating cascading interactions of bewildering complexity. A force that would rather tear brand new matter into existence from the energy of empty space than allow a single quark to walk free. That force has a name. It's called the strong nuclear force, and it is governed by a theory called quantum chromodynamics. To understand why quarks can never be alone, you first have to understand the force that holds them together. And to appreciate just how strange that force is, you need to understand how all the other forces in nature work. Because the strong force breaks every single rule the others follow. It's not just different in degree, it's different in kind. And that difference is what makes confinement not just possible, but inevitable. Physics has identified 4 fundamental forces that govern everything in the universe: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. These 4 forces are responsible for every interaction between every particle of matter that has ever existed. Every push, every pull, every attraction, every repulsion, every orbit, every bond, every decay, every single thing that happens in the physical universe is caused by one of these 4 forces. There is nothing else. No 5th force hiding in the shadows, as far as over. A century of precise experimental measurements can tell us these 4 are all there are. So let's look at each one, starting with the most familiar. Because understanding how they work will make the strong force's strangeness hit that much harder. Gravity is the one you know best. It's the force that keeps your feet on the ground, that keeps the Earth orbiting the Sun, that holds galaxies together across millions of light years. Gravity is always attractive. It only pulls. It never pushes. Every object with mass attracts every other object with mass. The more massive the objects and the closer they are, the stronger the gravitational pull. Isaac Newton described gravity mathematically in 1687 with his law of universal gravitation, and Albert Einstein refined our understanding with general relativity in 1915, showing that gravity is actually the curvature of space-time caused by mass and energy. A bowling ball placed on a stretched rubber sheet creates a dip, and a marble rolling nearby curves toward it. That's a rough picture of how mass curves space-time and creates what we experience as gravity. Gravity is by far the weakest of the 4 forces. It might not feel weak when you trip and hit the ground, but that's only because the entire Earth is pulling on you. The gravitational attraction between 2 individual protons is about 10 to the power of 36 times weaker than the electromagnetic force between them. That's a 1 followed by 36 zeros times weaker. If you held 2 protons a certain distance apart, the electromagnetic repulsion pushing them away from each other would be a trillion times stronger than the gravitational attraction pulling them together. Gravity only becomes significant when you have enormous amounts of mass, like planets, stars, and galaxies. At the scale of individual particles, gravity is essentially irrelevant. Physicists usually ignore it entirely when studying particle interactions because its effects are so incredibly small compared to the other forces. Electromagnetism is the force you interact with constantly, even if you don't realize it. Every time you see light, that's electromagnetism. Every time you feel the solidity of a surface, that's the electromagnetic repulsion between electrons in your skin and electrons in the surface. Every time you pick up an object, the friction and normal forces keeping it in your hand are electromagnetic. Chemistry is fundamentally electromagnetic. The bonds between atoms, the reactions that power your metabolism, the structure of DNA, the electrical signals in your brain, all electromagnetic. Light, radio waves, microwaves, X-rays, they're all electromagnetic radiation, differing only in wavelength and frequency. Electromagnetism is arguably the most important force for everyday life, governing virtually every phenomenon you experience, except the force of gravity pulling you downward. Electromagnetism is carried by photons. When two charged particles interact electromagnetically, they exchange photons. One particle emits a photon, the other absorbs it, and this exchange creates the force between them. This is a crucial concept in modern physics. Forces aren't mysterious, invisible threads connecting objects. They're carried by specific particles called gauge bosons. The gauge boson of electromagnetism is the photon, the same particle that makes up light. Electromagnetism can be either attractive or repulsive. Opposite charges attract, like charges repel. This is why electrons are attracted to protons, because electrons are negative and protons are positive. And this is why two electrons repel each other, because they're both negative. The strength of the electromagnetic force decreases with distance. If you double the distance between two charges, the force drops to 1/4 of its original strength. This is called the inverse square law. It means electromagnetism weakens rapidly as things move apart. At large distances, the electromagnetic force between two charges becomes negligible. And here's something critical about photons. Photons are electrically neutral. They carry no electric charge. This means photons don't interact with each other through electromagnetism. Two beams of light can pass right through each other without any interaction. You can shine two flashlights so the beams cross, and the photons in each beam will pass through the other beam as if it weren't there. This might seem like a minor technical detail, but it turns out to be one of the most important differences between electromagnetism and the strong force. Remember this, it's going to matter enormously. The weak nuclear force is responsible for certain types of radioactive decay. It's the force that allows a neutron to transform into a proton by emitting an electron and an antineutrino. This process is called beta decay, and it's crucial for many nuclear reactions, including some of the reactions that power the sun. The weak force is carried by three massive gauge bosons called the W+, W-, and Z bosons. These particles are extremely heavy, roughly 80 to nearly 100 times the mass of a proton. Because the carrier particles are so massive, the weak force has an extremely short range. It only operates over distances of about 1/1000th of the diameter of a proton. Beyond that, it effectively doesn't exist. The weak force is important for certain particle transformations, but it doesn't hold anything together. It's a force that changes particles from one type to another, rather than binding them. Now we come to the strong nuclear force. The strong force is the most powerful force in nature. It's about 100 times stronger than electromagnetism at the distances where it operates, about 10 to the power of 6 times stronger than the weak force, and about 10 to the power of 38 times stronger than gravity. It is overwhelmingly, incomparably, staggeringly the strongest force in the universe. The strong force is what holds quarks together inside protons and neutrons, and a residual effect of the strong force, a kind of spillover, is what holds protons and neutrons together inside atomic nuclei. Without the strong force, protons couldn't exist. Neutrons couldn't exist. Atomic nuclei couldn't exist. Atoms couldn't exist. You couldn't exist. Nothing made of matter could exist. The strong force is the foundation of all material reality, and the theory that describes the strong force is called quantum chromodynamics, or QCD. The word chromodynamics comes from the Greek word chroma, meaning colour, because, as we discussed, the charge associated with the strong force is called colour charge. Just as electromagnetism is the theory of electric charges and their interactions through photon exchange, quantum chromodynamics is the theory of colour charges and their interactions through the exchange of a different kind of particle. That particle is called the gluon. The name tells you exactly what it does. It glues quarks together. Just as photons carry the electromagnetic force between electrically charged particles, gluons carry the strong force between color-charged particles. When two quarks interact through the strong force, they do so by exchanging gluons. One quark emits a gluon, the other absorbs it, and this exchange creates the binding force between them. But here is where everything changes. Here is where the strong force departs radically from every other force in nature. And this departure is so fundamental, so profound in its consequences, that it creates phenomena found nowhere else in physics. Photons, the carriers of electromagnetism, are electrically neutral. They don't carry the charge of the force they transmit. A photon can carry a force between two electrons, but the photon itself has no electric charge. It doesn't feel the electromagnetic force in the same way charged particles do. Photons don't attract or repel each other electromagnetically. They're neutral messengers, impartial carriers. They deliver the force without being subject to it. Gluons are completely different. Gluons carry color charge. Let me say that again because it's the single most important fact for understanding everything that follows. The particles that carry the strong force are themselves charged under the strong force. Gluons are not neutral messengers, they're charged participants. They don't just transmit the force, they feel it. They interact with each other through the very force they carry. This is as if postal workers were not just delivering letters, but were themselves constantly writing and sending letters to each other, creating an ever-growing cascade of communication that gets more complex the more you try to track it. The messengers are also the message senders and receivers. There's no separation between the force and the force carriers. In electromagnetism, force lines spread out smoothly between two charges. The electric field extends in all directions, getting weaker and weaker with distance. It's simple, it's clean, it's predictable. But in QCD, the gluons that create the force field between two quarks also interact with each other. They pull on each other. They exchange more gluons among themselves. And this self-interaction fundamentally changes the behavior of the force. Let me explain what happens in more mathematical detail, because this is where the magic happens. In quantum field theory, when we talk about forces, we talk about something called the coupling constant. This is essentially a number that tells you how strong a force is. For electromagnetism, the coupling constant is called the fine structure constant, and its value is approximately 1 over 137. This is a small number, which is why electromagnetic interactions are relatively straightforward to calculate. Each additional photon exchange in an electromagnetic interaction adds a factor of about 1 over 137 to the calculation, making higher order corrections small and manageable. But here's the deep insight. The coupling constant isn't truly constant. It changes depending on the energy of the interaction, or equivalently, depending on the distance scale you're probing. For electromagnetism, this effect is subtle. The electromagnetic coupling constant increases slightly at higher energies, meaning at shorter distances. This happens because of a phenomenon called vacuum polarization. Empty space, the vacuum, isn't really empty. Quantum mechanics tells us that particle-antiparticle pairs are constantly popping in and out of existence everywhere in the vacuum, existing for incredibly brief moments before annihilating each other. These virtual particles are real. They have measurable effects. Around an electron, these virtual pairs arrange themselves so that the positive partners are slightly closer to the electron and the negative partners are slightly farther away. This screens the electron's charge, making it appear weaker at large distances and stronger at short distances. If you probe an electron from far away, the virtual particle cloud partially hides its true charge. As you get closer, you see through the cloud and the charge appears stronger. For electromagnetism, this screening effect is small and gradual. The electromagnetic coupling constant changes only slightly across enormous ranges of energy. It's a subtle correction that matters for precision calculations, but doesn't fundamentally change how the force behaves. For the strong force, the situation is completely, dramatically, revolutionarily different. In QCD, the vacuum is also filled with the virtual quark-antiquark pairs, and these do screen the color charge of a quark, just like virtual electron-positron pairs screen electric charge. If this were the only effect, the strong force would behave similarly to electromagnetism. Stronger at short distances, weaker at long distances. Simple enough. But there's another effect in QCD that doesn't exist in electromagnetism. Because gluons carry color charge, the vacuum is also filled with virtual gluon pairs. And these virtual gluons don't screen the color charge. They anti-screen it. They do the opposite of screening. Instead of partially hiding the color charge, the virtual gluon cloud amplifies it. This effect is so strong that it overwhelms the screening from the virtual quark-antiquark pairs and completely reverses the behavior of the force compared to what you'd naively expect. The result is that the strong force coupling constant runs in the opposite direction from the electromagnetic coupling constant. As you increase the energy, as you probe shorter and shorter distances, the strong coupling constant gets smaller. The force gets weaker at short distances. And as you decrease the energy, as you probe longer and longer distances, the coupling constant gets larger. The force gets stronger at large distances. This is utterly backwards compared to every other force you've ever encountered. Gravity gets weaker with distance. Electromagnetism gets weaker with distance. Even the weak force, though its short range is due to the mass of its carrier particles, rather than the distance dependence of the coupling, effectively gets weaker at larger separations. Every force in your daily experience gets weaker as things move apart, but the strong force gets stronger. This behavior has a name. The weakening of the strong force at short distances is called asymptotic freedom. It was discovered in 1973 by David Gross, Frank Wilczek, and David Politzer, and it won them the Nobel Prize in Physics in 2004. Their discovery was one of the most important breakthroughs in the history of particle physics, because it explained something that had deeply confused physicists for years. It also completed QCD as a consistent theory, giving physicists confidence that quantum chromodynamics was the correct description of the strong force. Before the discovery of asymptotic freedom, many physicists doubted that a quantum field theory could describe the strong force at all, because the force seemed too powerful and too complex for the standard mathematical tools. Asymptotic freedom showed that QCD was not only viable, it was the only type of theory that could explain both the strong binding of quarks at large distances and their apparent freedom at short distances. The deep inelastic scattering experiments at Stanford in the late 1960s had shown that quarks inside protons behave almost as if they're free particles. When you fire a high-energy electron at a proton, the electron interacts with the individual quarks inside, and those quarks respond as if they're barely interacting with each other. This was bizarre. Quarks were supposed to be tightly bound inside protons. The strong force was supposed to be incredibly powerful. So why did the quarks act as if they were barely bound? Asymptotic freedom provided the answer. At the very short distances probed by high-energy collisions, the strong force becomes weak. Quarks that are very close together barely feel the strong force at all. They move almost freely, like independent particles rattling around inside the proton. This is why the deep inelastic scattering experiments saw what they saw. The high-energy electrons were probing such short distances that the quarks appeared nearly free. But this freedom is an illusion. It only exists at extremely short distances. As the distance between quarks increases, the strong force grows, rapidly, relentlessly, without limit. There is no escape from this increasing force. The farther you try to pull two quarks apart, the harder the force pulls them back together. Let me give you an analogy. Though I want to be clear that no analogy perfectly captures what's happening. Imagine two quarks connected by a spring. With a normal spring, there's a rest position where the spring exerts no force. Pull the ends apart a little, and the spring pulls back gently. Pull them apart more, and the spring pulls back harder. That part is similar to the strong force. But with a normal spring, there's a breaking point. Pull hard enough, and the spring snaps. The two ends fly apart, and the force is gone. The strong force doesn't work like that. There is no breaking point in the usual sense. The force just keeps getting stronger and stronger and stronger the farther apart you pull the quarks. The spring never snaps in the way you would expect. Something else happens instead. Something far more dramatic. But we'll get to that in detail later. What causes this bizarre distance dependence? The answer goes back to gluon self-interaction. In electromagnetism, the force field between two charges spreads out in all directions. The field lines emanate from a positive charge and terminate on a negative charge, fanning out through space. As you move the charges farther apart, the field lines spread over a larger volume, and the force weakens. This is why electromagnetism follows the inverse square law. But in QCD, the gluon field between two quarks doesn't spread out. Because gluons interact with each other, the field lines attract each other. They pull together. Instead of fanning out through space, the gluon field between two quarks squeezes into a narrow tube. A concentrated string of gluon energy connecting the two quarks. Physicists call this a flux tube, or sometimes a color flux tube, or even a QCD string. Think about what this means. In electromagnetism, when you pull two charges apart, the field spreads out and weakens. The field lines fan out into the surrounding space, covering more and more volume, and the energy density drops. In QCD, when you pull two quarks apart, the field doesn't spread out. It stays concentrated in a tube. The gluon self-interactions are like hands squeezing the field lines together, preventing them from fanning out. The tube gets longer as the quarks move apart, but it doesn't get wider. Its cross-section stays roughly constant, about 1 femtometer across, roughly the size of a proton. And because the tube stores energy per unit length, about 1 giga-electron-volt per femtometer, which translates to roughly 14 tons of force, a longer tube means more energy. More energy means a stronger restoring force trying to pull the quarks back together. 14 tons of force between two particles smaller than an atom. That's the strong force. The energy stored in this flux tube increases roughly linearly with distance. If you double the separation between the quarks, you roughly double the energy stored in the tube. This linear increase in energy is what creates the confining potential. It's what makes it impossible to isolate a quark. Because energy keeps increasing as separation increases, you'd need infinite energy to pull a quark infinitely far from its partners. And infinite energy doesn't exist. This is fundamentally different from electromagnetism, where the energy stored in the field between two charges approaches a finite limit as you pull them apart. Eventually, with enough energy, you can fully separate two electric charges. The electron can fly free from the proton. You can ionize an atom by providing enough energy to overcome the electromagnetic binding. But you can never provide enough energy to overcome the strong force binding between quarks, because the energy required grows without bound. The gluon self-interaction creates something else remarkable. In electromagnetism, there are only photons, one type of force carrier. It's electrically neutral, and it doesn't interact with other photons. Clean and simple. In QCD, there are 8 different types of gluons. 8. Not 1, not 3, but 8. This number comes from the mathematics of the color charge symmetry, which is described by a mathematical structure called SU3. Without going too deep into group theory, the 8 gluons arise because of how the 3 color charges and 3 anti-color charges can be combined. Each gluon carries a combination of a color and an anti-color. For example, one gluon might carry red anti-blue. Another might carry green anti-red. These combinations mean that when a gluon is exchanged between two quarks, the colors of the quarks can change. A red quark can emit a red anti-blue gluon and become a blue quark. The blue quark that absorbs the gluon becomes red. The quarks are constantly swapping colors through gluon exchange, changing from red to blue to green and back again in a ceaseless quantum shuffle. This color swapping means that if you could somehow take a snapshot of the quarks inside a proton at any instant, you'd see one red, one green, and one blue. But if you took another snapshot a moment later, the colors would have shifted. The quarks would still add up to color neutral, still one of each color, but which quark had which color would have changed. The overall neutrality is maintained, but the individual colors are in constant flux. And because each of those 8 gluons carries color charge, each gluon can emit and absorb other gluons. A gluon traveling between 2 quarks can spontaneously split into 2 gluons. Those 2 gluons can each split again. They can recombine. They can interact with each other in increasingly complex ways. The space between 2 quarks isn't just filled with a simple force field. It's a seething, roiling, fantastically complex web of gluon interactions. This complexity is why QCD is so difficult to calculate. In electromagnetism, you can calculate the force between two charges with extraordinary precision because the photon is neutral and the calculations are manageable. Each additional layer of complexity, each additional virtual photon, adds only a small correction. The calculations converge quickly and you get excellent answers. In QCD, each additional layer of gluon interaction is not a small correction. At low energies and large distances, where the coupling constant is large, each additional gluon exchange contributes significantly. The calculations don't converge. You can't just add up a few terms and get a good answer. The entire sum matters, and that sum includes an infinite number of increasingly complicated gluon interactions. This mathematical intractability is one of the reasons why QCD took so long to develop, and why some of its predictions are still difficult to compute today. To handle these calculations, physicists often resort to a technique called lattice QCD, where they discretize space-time into a grid of points and use supercomputers to numerically simulate the behavior of quarks and gluons. These simulations require enormous computing power. Some of the most powerful supercomputers on Earth are dedicated to lattice QCD calculations, but the results have been extraordinary. They've confirmed the predictions of QCD with impressive accuracy, including predicting the masses of various hadrons to within a few % of their measured values. So let's summarize what makes the strong force unique among all the forces in nature. First, its carrier particles, gluons, carry the charge of the force they transmit. This is completely unlike photons in electromagnetism, which are electrically neutral. Photons deliver the electromagnetic force without being subject to it. They're bystanders, neutral couriers. Gluons are both the messengers and the participants. This single difference changes everything about how the force behaves. Second, because of gluon self-interaction and the resulting anti-screening, the strong force gets stronger with distance and weaker at short range. This is the opposite of every other force. It means quarks that are close together are nearly free, but quarks that are far apart are bound more and more tightly. Third, the gluon. Field between quarks doesn't spread out into space like electromagnetic field lines. It collapses into a narrow flux tube that stores energy proportional to its length. This creates a confining potential that grows without bound as quarks are separated. Fourth, the force is mediated by 8 types of gluons rather than a single type of carrier particle, and these gluons constantly change the color charges of the quarks they connect, creating a dynamic, shifting web of interactions. These 4 properties combine to create a force that is fundamentally, qualitatively different from anything else in all of physics. It's not just a stronger version of electromagnetism. It's not just electromagnetism with more types of charge or more complex mathematics. It's a completely different kind of force with completely different behavior. The mathematics is different, the distance dependence is different, the carrier particle behavior is different, the consequences are different, everything is different. And the most important consequence of all these differences is confinement, the absolute, inescapable, permanent imprisonment of quarks inside composite particles. Quarks cannot be freed. The very nature of the strong force makes their isolation impossible. The stronger you pull, the stronger the force resists. The more energy you pour in, the more the universe pushes back. And when you finally pour in so much energy that something has to give, the universe does something extraordinary. Something almost magical in its elegance. something that shows just how deeply the laws of physics conspire to keep quarks bound together. The universe creates new quarks, not from nothing, from the energy itself. The energy you poured in trying to separate the quarks gets converted into matter, into brand new quarks and antiquarks that immediately bind with the originals, forming new composite particles. You started by trying to pull 2 quarks apart. You end up with 4 quarks, or 6, or 8, all neatly paired up in color-neutral combinations. You've created new matter, but you haven't freed a single quark. This process, this absolute refusal of the universe to allow a quark to exist alone, is the phenomenon of confinement. And understanding exactly how it works, step by step, is where we're going next. Because what happens when you try to pull quarks apart is one of the most remarkable sequences of events in all of nature. And it reveals something deep and beautiful about the fundamental structure of reality. Now we arrive at the heart of everything. The phenomenon that makes quarks unlike any other particle in the universe. The reason you will never, not in a billion years, not with infinite funding, not with technology 1,000 generations more advanced than ours, hold a single quark in your hand. This phenomenon is called confinement, and it's not a barrier we haven't yet figured out how to overcome. It's not an engineering challenge waiting for a breakthrough. It's not a limitation of our current particle accelerators or our current level of understanding that some future Einstein might solve. It is a fundamental consequence of quantum chromodynamics, written into the deepest laws of the universe with the same finality as the conservation of energy or the impossibility of traveling faster than light. Confinement is not something that prevents us from isolating quarks. Confinement is the universe's absolute declaration that isolated quarks cannot exist. The distinction matters. It's not that we can't find them. It's that there is nothing to find. Let me walk you through exactly what happens when you try to separate 2 quarks, step by step. Because the sequence of events is one of the most extraordinary things in all of physics. Start with a proton. Inside that proton are 3 quarks, 2 up quarks and 1 down quark. They're not sitting still. They're moving around inside the proton at tremendous speeds, bouncing off each other, exchanging gluons constantly, their colors shifting from red to green to blue in an endless quantum dance. The proton is about 1 femtometer across, which is 1 quadrillionth of a meter, or about 100,000 times smaller than an atom. That's the space these 3 quarks share. And within that tiny volume, they're relatively comfortable. The strong force between them is actually quite manageable at these short distances. Remember asymptotic freedom. At short distances, the strong coupling constant is small. The quarks are close together, and the force between them is moderate. They can move around inside the proton with a surprising degree of freedom, almost as if they're barely bound. This is why experiments that probe the inside of protons at high energies see quarks behaving nearly like free particles. At the scale of the proton's interior, the strong force is present but restrained, almost gentle by its own standards. Now imagine you reach in and grab one of those quarks. Not literally, of course. Quarks are far too small to grab physically. But imagine you could somehow apply a force to 1 quark, pulling it away from the other 2. What happens? At first, as you begin to pull, the quark moves slightly away from its partners. The distance between them increases by a tiny amount, and as it does, the gluon field between the quarks begins to change. Remember the flux tube we discussed? The gluon field between quarks doesn't spread out into space the way an electric field does. It collapses into a narrow tube of concentrated energy connecting the quarks. As you pull one quark away, this tube stretches. It gets longer, but it doesn't get wider. The gluon self-interactions keep the field lines squeezed together in a tight bundle about 1 femtometer in diameter. And here's the critical thing. That tube stores energy. About 1 gigaelectronvolt of energy per femtometer of length. This is an enormous energy density. 1 gigaelectronvolt per femtometer translates to roughly 14 metric tons of force between two particles that are each smaller than a billionth of a meter. The amount of energy packed into that tiny string of gluon field is staggering. And as you pull the quark farther away, the tube gets longer and the total energy stored in it increases. Pull the quark 1 femtometer away and the tube stores about 1 gigaelectronvolt of energy. Pull it 2 femtometers away and the tube stores about 2 gigaelectronvolts. 3 femtometers, 3 gigaelectronvolts. The relationship is roughly linear. Double the distance and you roughly double the energy. This is completely unlike electromagnetism. If you pull an electron away from a proton, the energy required increases at first, but it levels off. There's a finite amount of energy you need to completely separate an electron from a proton. It's 13.6 electron volts for a hydrogen atom. Once you've supplied that much energy, the electron is free. It can fly away to infinity, and the atom is ionized. The energy cost approaches a maximum, and then stops growing. The electron is liberated. But with a strong force, the energy cost never levels off. It just keeps growing. 1 gigaelectronvolt per femtometer, indefinitely. There is no ionization energy for quarks. There's no amount of energy you can supply to say, there, the quark is now free. The energy just keeps climbing the farther you pull. If you could somehow pull a quark just 1 centimeter away from its partners, the flux tube would store roughly 10 trillion gigaelectronvolts of energy. That's about 1,000 times more energy than was involved in the proton-proton collisions at the Large Hadron Collider, the most powerful particle accelerator ever built. And 1 centimeter is nothing. It's the width of your fingernail. In everyday terms, 1 centimeter is absurdly small. But in the world of quark confinement, pulling a quark 1 centimeter away would require more energy than humanity's most powerful machine has ever concentrated into a single collision. That's how powerful the strong force becomes at everyday distances. But here's what actually happens. You never get anywhere close to pulling a quark a meter away. Because long before that, long before the energy in the flux tube reaches those absurd levels, something remarkable occurs. As the flux tube stretches and the energy stored in it increases, there comes a point where the energy in the tube is enough to create new particles. Specifically, the energy becomes sufficient to create a new quark-antiquark pair. Remember Einstein's famous equation, E equals mc squared. Energy and mass are interchangeable. If you have enough energy concentrated in a small enough region, that energy can spontaneously convert into matter. A particle and its antiparticle can pop into existence from pure energy, as long as the energy is sufficient to account for their combined mass. The lightest quarks, the up and down quarks, have masses of only a few megaelectronvolts each. Creating a quark-antiquark pair requires at least twice the quark mass, so roughly 5 to 10 megaelectronvolts of energy. But the flux tube is storing energy at a rate of about 1 gigaelectronvolt per femtometer, which is 1,000 mega electron volts per femtometer. That means by the time the quarks have been separated by even a tiny fraction of a femtometer beyond their normal range, there's already more than enough energy in the flux tube to create new quark-antiquark pairs. And this is exactly what happens. The flux tube doesn't just store energy passively. When the energy density in the tube reaches a critical threshold, the tube snaps. But it doesn't snap like a rubber band, leaving two free ends. It snaps by converting its energy into a new quark-antiquark pair right at the breaking point. The tube breaks, and at each broken end, a brand new quark or antiquark appears, created from the energy that was stored in the tube. Let me describe this more carefully, because the details matter. You started with a quark that you were pulling away from its partners. As you pulled, a flux tube formed between it and the quarks it left behind. The tube stretched, storing more and more energy. Then the tube snapped. At the point where it broke, a new quark-antiquark pair was created. The new antiquark attaches to the quark you were pulling, forming a meson. The new quark joins the original quarks you left behind, either forming a new baryon or participating in further rearrangements. Instead of isolating a quark, you've created a new hadron. The quark you were trying to free is now bound in a meson, happily paired with its brand new antiquark partner. It was never alone, not for a single instant. The moment the tube snapped, the new particles appeared, and the quark was immediately confined again in a new color-neutral combination. This process is called hadronization, or sometimes string breaking, and it's not theoretical speculation. It's observed every single day in particle accelerators around the world. At the Large Hadron Collider at CERN, protons are smashed together at energies of 13 teri-electron volts, which is 13 trillion electron volts. These collisions are among the most violent events humans have ever created. When two protons collide at these energies, the quarks and gluons inside them are scattered in all directions. Individual quarks are blasted away from each other with enormous kinetic energy. They fly apart at nearly the speed of light, separating rapidly. And as they separate, flux tubes form between them, stretching, storing energy, exactly as we described. Then the flux tubes snap, not once, but many times, in a cascade. Each snap creates a new quark-antiquark pair. Those new quarks also fly apart, forming more flux tubes that snap again, creating more pairs. The process cascades, with tubes forming and breaking over and over in a shower of particle creation. The result is something physicists call a jet. A jet is a narrow spray of hadrons, dozens or even hundreds of mesons and baryons, all flying in roughly the same direction. Each jet traces the path of an original quark or gluon that was knocked out of the proton in the collision. But you never see the quark itself. By the time the particles reach the detectors, the original quark has been buried inside hadrons, buried in mesons and baryons created by the flux tube breaking process. Surrounded by a shower of newly created particles, all color neutral, all perfectly confined. The detectors at the LHC record jets, not quarks. They see pions, kaons, protons, neutrons, and other hadrons. They never see a bare quark. The quarks are always hidden, always confined, always bound. This has been confirmed in every single high-energy collision experiment ever performed. CERN, Fermilab, SLS, Brookhaven, DESY, KEK, every major particle physics laboratory in the world that has collided particles at high energies has observed the same thing. Quarks are produced. They fly apart. Flux tubes form. The tubes snap. new particles are created, jets of hadrons emerge, and no free quark is ever detected. Not once in decades of experiments involving trillions upon trillions of collisions. Let me tell you about one of the most telling details from the deep inelastic scattering experiments we discussed earlier. Remember, those were the experiments at Stanford where physicists fired high-energy electrons at protons and discovered the quarks inside. What's easy to overlook is what those experiments also revealed about confinement. The electrons interacted with individual quarks. They transferred enormous momentum to them. They could effectively tag a specific quark inside the proton, measure its properties, track its recoil. The quarks were right there, as real and measurable as anything in physics. But not a single quark was ever knocked free. Every quark that absorbed momentum from an incoming electron was recaptured. Every one that recoiled from a collision ended up inside a hadron. Physicists could see the quarks. They could measure them, but they could never extract them. It was like being able to see a prisoner through the bars, measure their height and weight, even hand them objects through a slot, but never open the cell door. The quarks were undeniably real and undeniably trapped. Later experiments at higher energies saw the same pattern, but even more dramatically. When the collision energy was high enough, the struck quark was blasted violently away from the other quarks in the proton. It carried enormous momentum and moved at nearly the speed of light in one direction. But as it flew away, the flux tube stretched and snapped, creating a jet of hadrons. On the opposite side, the remnants of the proton also produced hadrons. The experiment saw two jets of particles flying in opposite directions, perfectly consistent with a quark being struck and flying away and then being confined through hadronization. The quark's presence was unmistakable. Its trajectory was clear, its momentum was measurable, but the quark itself was never naked. It was always dressed in newly created particles by the time it reached the detector. There's an even more vivid demonstration of confinement that comes from electron-positron collisions. When an electron and a positron, which is the antimatter partner of an electron, collide at high energy, they annihilate each other completely. Every bit of their mass and all of their kinetic energy is converted into pure energy in the form of a virtual photon or Z-boson. For a fleeting instant, matter is gone entirely. There are no particles. There's only energy. Then that energy converts back into matter, producing a quark and an antiquark flying in opposite directions at nearly the speed of light. These are freshly created particles, conjured from pure energy by E equals mc squared. And the moment they exist, they're already doomed to be confined. Think about what happens next. You have a quark flying one way and an antiquark flying the other way. They're moving apart rapidly. A flux tube forms between them. It stretches. It stores energy. It snaps. New quark-antiquark pairs are created at the breaking points. Those new quarks form flux tubes with each other. Those tubes stretch and snap too. The cascade continues until all the energy has been converted into hadrons. The result is two jets of hadrons flying in opposite directions, one tracing the path of the original quark and one tracing the path of the original antiquark. Two jet events from electron-positron annihilation had first been observed at SPEAR, the collider at the Stanford Linear Accelerator Center, in the mid-1970s. They confirmed that quarks were real, but it was at higher energies, at the Petra Accelerator at Dessau in Hamburg, Germany, that something new appeared. But the story gets even better. Sometimes, In these electron-positron collisions, one of the quarks radiates a high-energy gluon before the hadronization process begins. This is similar to how an accelerating electric charge radiates a photon, except here a color-charged quark radiates a color-charged gluon. The gluon flies off in a different direction from the quark and antiquark, carrying a significant fraction of the total energy. And because the gluon carries color charge, it also produces a jet of hadrons through the same flux tube mechanism. The result is a 3-jet event. 3 sprays of hadrons flying in 3 different directions. 1 jet from the quark, 1 jet from the antiquark, 1 jet from the gluon. 3 jet events were first observed at Petra in 1979, and they provided the first direct experimental evidence for the existence of gluons as real physical particles. Before that, gluons have been predicted by QCD but never directly observed. The 3 jet events proved that gluons were real objects that carried color charge, produced jets through hadronization, and underwent confinement just like quarks. Let me emphasize something here that's easy to miss. Gluons are also confined. It's not just quarks that can't exist alone. Gluons, because they carry color charge, are also subject to confinement. You will never detect a free gluon any more than you'll detect a free quark. When a gluon is produced in a high-energy collision, it immediately undergoes hadronization, producing a jet of color-neutral hadrons. The gluon is always hidden inside composite particles by the time it reaches a detector. Both quarks and gluons are permanently imprisoned by the very force they generate. Now, I want to address a question that might have occurred to you. If the energy in the flux tube increases linearly with distance, and if the flux tube always snaps and creates new particles, is there any way to beat the system? Can we somehow provide so much energy so quickly that we can pull a quark away before the tube has time to snap? The answer is no, and the reason is fundamental. The process of quark-antiquark pair creation from the flux tube doesn't require any special conditions or any time to build up. It's a quantum mechanical process, governed by the probabilistic laws of quantum field theory. As soon as the energy in the flux tube exceeds the threshold needed to create a quark-antiquark pair, the probability of pair creation becomes significant. And because the threshold is so low, just a few mega electron volts for the lightest quarks, while the energy in the tube builds at roughly 1 giga electron volt per femtometer, the tube barely has to stretch at all before pair creation kicks in. The snap happens almost instantly, almost simultaneously with the stretching. There's no window of opportunity, there's no gap you can exploit. Even in the most extreme collisions at the Large Hadron Collider, where quarks are blasted apart with 13 tera electron volts of energy, the confinement process keeps pace. The quarks separate, the tubes form, the tubes break, new particles appear. It all happens on a timescale of about 10 to the negative 24 seconds. That's a yoctosecond, roughly the time it takes light to cross the diameter of a proton. The universe's confinement mechanism operates at the speed of light itself. You cannot outrun it because nothing can outrun it. There is no trick, no shortcut, no technological advance that will ever change this. It's built into the structure of space-time and quantum field theory at the most fundamental level. People have searched for free quarks. Seriously, methodically, exhaustively searched. Because physics is an experimental science, and even when theory tells you something is impossible, you check anyway. That's how science works. You test everything. In the 1960s and 70s, Before confinement was well understood, many physicists expected that with enough energy, quarks could be knocked free from protons. They designed experiments specifically to look for fractionally charged particles. Since a free quark would carry a charge of either positive 2/3 or negative 1/3, these fractional charges would be unmistakable. Every other known particle carries a whole number charge. A particle with 2/3 of an electron's charge would stand out like a beacon. Physicists searched in cosmic rays, the high-energy particles that rain down on Earth from space. Some cosmic rays carry energies millions of times greater than anything the Large Hadron Collider can produce. They arrive from violent astrophysical sources, supernova remnants, active galactic nuclei, events of unimaginable power. If extreme energy could free a quark, cosmic rays would be the place to find them. Physicists built dedicated detectors, placed them on mountaintops and in underground laboratories, ran them for years. They found nothing. No fractionally charged particles, no free quarks, not one. They searched in accelerator experiments, combing through the debris of billions of high-energy collisions. They found nothing. They searched in matter itself. William Fairbank at Stanford University conducted an extremely precise experiment in the 1970s and 80s using tiny superconducting niobium spheres cooled to near absolute zero. He measured the electric charge on these spheres with extraordinary precision, looking for any sphere that carried a fractional charge, which would indicate a trapped quark sitting inside the material. Fairbank initially reported some positive results, measurements that seemed to show fractional charges on a few spheres. The physics community held its breath, but other groups attempted to reproduce the results using similar and even more sensitive techniques, and they found nothing. Subsequent experiments with higher precision found no evidence of fractional charges in matter. The consensus is that there are no free quarks trapped in ordinary materials. They searched in meteorites, in ocean water, in lunar samples brought back by the Apollo missions. They searched using magnetic monopole detectors that would also be sensitive to fractionally charged particles. They searched with dedicated detectors at multiple particle accelerators. Decades of searching across every environment physicists could access produced the same result every single time. No free quarks, not one. This isn't a case of we haven't looked hard enough. This is a case of having looked exhaustively with every tool available, in every environment imaginable, and finding exactly what QCD predicts. Quarks are confined, always, everywhere, without exception. The mathematical understanding of confinement is, it must be said, incomplete. This is one of the great unsolved problems in theoretical physics. We have overwhelming experimental evidence that confinement is real. We have lattice QCD calculations that reproduce confinement beautifully on supercomputers. We have the qualitative understanding of flux tubes, gluon self-interaction, and the linear confining potential, but a complete, rigorous mathematical proof that QCD necessarily produces confinement, starting from the fundamental equations and deriving confinement as an exact consequence, has never been achieved. This problem is considered so important that the Clay Mathematics Institute has included it as one of the 7 Millennium Prize problems. The official problem is to prove that the quantum Yang-Mills theory, which is the mathematical framework underlying QCD, has a mass gap. A mass gap would mean that the lightest particle in the theory has a non-zero mass, which is related to confinement because it means you can't create massless, free-ranging gluon fields. Solving this problem comes with a prize of $1 million. As of now, nobody has claimed it. The problem has remained open since the year 2000. Some of the greatest mathematical physicists in the world have worked on it. And while there has been progress, a complete proof remains elusive. But the experimental reality of confinement is beyond any reasonable doubt. Lattice QCD calculations, performed on some of the most powerful supercomputers in the world, consistently show quarks being confined into hadrons. These calculations start from the fundamental equations of QCD, discretize space-time into a grid, and compute the behavior of quarks and gluons numerically. The results match experimental observations with remarkable precision. The masses of protons, neutrons, pions, and dozens of other hadrons predicted by lattice QCD agree with measured values to within a few percent. The confining potential extracted from lattice calculations shows exactly the linear behavior we'd expect from flux tubes. Everything is consistent. Theory, computation, and experiment all agree. Quarks are confined. There's something deeply poetic about confinement when you think about it. The fundamental building blocks of all matter, the smallest known components of everything you've ever seen or touched or loved, are particles that can never be alone. They exist only in relationship, only in combination, only together. A quark by itself is not just impractical to observe, it's not just extremely difficult to isolate, it's fundamentally, structurally, mathematically impossible to separate from its partners. The universe doesn't just make it hard to isolate a quark, the universe makes it meaningless. A single quark in isolation is as impossible as a north magnetic pole without a south magnetic pole, or a coin with only one side. The very attempt to isolate a quark creates more quarks. The energy you pour into pulling one quark away is converted to the mass of new quarks that immediately bind with the one you were trying to free. It's as if the universe has a rule, a deep, unyielding rule that says these particles must always be together. And any attempt to violate that rule, no matter how energetic, no matter how clever, will only result in the creation of more particles that satisfy it. You cannot break this rule. You can only create more evidence that it's unbreakable. Every proton in your body contains 3 quarks that have been confined since the first microseconds after the Big Bang. Those quarks have been bound together for 13.8 billion years. They've been inside atomic nuclei that formed in the cores of stars. They've been part of the interstellar dust that coalesced into our solar system. They've been in the rocks and water and air of Earth for 4.5 billion years. And not once in all that time, not once across the entire lifespan of the universe, has any of those quarks been alone. They've always been bound, always confined, always together, and it's not because nothing tried to separate them. Stars explode as supernovae, releasing energies that dwarf anything humans have ever created. Cosmic rays carry individual particles at energies millions of times beyond what the Large Hadron Collider can achieve. Neutron stars crush matter to densities where atoms cease to exist. In every one of these extreme environments, confinement holds, quarks remain bound, the flux tubes stretch and snap, new particles form. The rule is never broken. The universe's commitment to confinement is absolute and total. This brings us to a profound realization about the nature of matter itself. Everything you see around you, every solid object, every liquid, every gas, every star, every planet, all of it is made of particles that are themselves made of particles that cannot exist alone. The foundation of all material reality is a set of building blocks that are permanently, irrevocably bound together. The visible universe, in all its vastness and complexity, is constructed from prisoners. And the prison they inhabit is not a place. It's a law. A law so deep and so fundamental that even the universe's most violent events cannot override it. But confinement isn't the end of the story. It's actually the beginning of an even deeper mystery. Because when you start asking what confinement means for the mass of matter, for the energy that holds the universe together, and for what happens when you push confinement to its absolute limits, you discover something even more astonishing. Something that reveals that nearly everything you think you know about what gives matter its weight, its substance, its reality, is wrong. Now that you understand confinement, now that you know quarks can never be alone, let's explore what this means for everything else. Because confinement doesn't just imprison quarks, it shapes the very nature of matter. It determines why things have mass. It dictates the structure of every atom in the universe, and it hides a secret about your own body that might be the most astonishing fact in all of physics. You have mass. You weigh something. When you step on a scale, the number you see reflects the gravitational pull between your body and the Earth, which depends on the total mass of all the atoms in your body. And the mass of those atoms comes almost entirely from their nuclei, from the protons and neutrons packed together at the center of every atom. Electrons contribute almost nothing. A proton is about 1,836 times heavier than an electron. So when you ask where your mass comes from, the answer is clear. It comes from protons and neutrons. But where does the mass of a proton come from? This is where everything you think you know falls apart. A proton is made of 2 up quarks and 1 down quark. The up quark has a mass of about 2.2 mega electron volts. The down quark has a mass of about 4.7 mega electron volts. If you add up the masses of the quarks inside a proton, 2 up quarks and 1 down quark, you get 2.2 plus 2.2 plus 4.7, which equals 9.1 mega electron volts. But the mass of a proton is 938.3 mega electron volts. The quarks account for less than 1% of the proton's mass. Less than 1%. The quarks inside the proton contribute only about 9 million electron volts out of 938. Where does the other 99% come from? The answer is the strong force itself. The energy of the gluon field, the kinetic energy of the quarks whipping around inside the proton, the energy of the virtual quark-antiquark pairs constantly popping in and out of existence in the proton's interior. All of this energy contributes to the proton's mass through Einstein's E equals mc squared. Mass and energy are the same thing, just measured in different units. The energy of the strong force interactions inside the proton is enormous, and that energy manifests as mass. Let me say this as clearly as I can, because it's one of the most profound facts in physics. Nearly all of the mass of everything you've ever touched, everything you've ever seen, everything you've ever held or lifted or weighed, does not come from the fundamental particles that matter is made of. It comes from the energy of the force that binds those particles together. The quarks themselves are almost massless. The proton is heavy because the strong force is powerful. The energy of confinement, the energy stored in the gluon fields, and the frantic motion of quarks bouncing off the walls of their prison, That is what gives matter its weight. Your body contains roughly 7 billion atoms. Each atom has a nucleus full of protons and neutrons, and 99% of the mass of each proton and neutron comes not from quarks, but from the binding energy of the strong force. When you pick up a book, the weight you feel in your hand is almost entirely the energy of gluon fields. When you stand on a scale, the number you read is almost entirely the mass equivalent of strong force energy. The ground you stand on, the chair you sit in, the food you eat, at the stars in the sky, nearly all of their mass is gluon energy made tangible through E equals mc squared. This has been confirmed by lattice QCD calculations. When physicists simulate protons on supercomputers, starting from the fundamental equations of QCD and computing the total energy of the quarks and gluons inside, they get a proton mass that matches the experimentally measured value. The calculation works only when you include the energy of the gluon field and the kinetic energy of the quarks. If you just add up the quark masses alone, you get the wrong answer by a factor of about 100. The strong force energy is not a minor correction. It is the dominant contribution. It is, for all practical purposes, where mass comes from. This also explains something that puzzled physicists for a long time. Why are protons and neutrons so much heavier than the quarks inside them? And why are their masses so similar to each other? A proton, made of 2 up quarks and 1 down quark, has a mass of 938.3 mega electron volts. A neutron, made of 1 up quark and 2 down quarks, has a mass of 939.6 mega electron volts. The difference is only about 1.3 mega electron volts. That's tiny. The proton and neutron are almost exactly the same mass, even though they contain different quarks. The reason is that the quark masses are almost irrelevant. The overwhelming majority of both the protons and neutrons' mass comes from the same source, the strong force binding energy. Since both particles are bound by the same force in similar configurations, they end up with almost identical masses. The small difference comes from the slight mass difference between up and down quarks and from electromagnetic effects, but these are tiny corrections on top of the dominant strong force contribution. Now let's talk about the full zoo of hadrons, the particles that quarks build when they're confined together. We've mentioned baryons and mesons, but let's explore them more carefully because the variety is remarkable, and it all stems from the rules of confinement. Baryons are particles made of 3 quarks, 1 of each color, red, green, and blue, adding up to color neutral. The most familiar baryons are the proton and neutron, but there are many others. The lambda baryon contains an up quark, a down quark, and a strange quark. It's heavier than a proton because the strange quark is heavier than the up and down quarks. The sigma baryons come in 3 varieties: sigma plus, sigma 0, and sigma minus, each containing different combinations of up, down, and strange quarks. The chi baryons contain 2 strange quarks. The omega minus baryon contains 3 strange quarks. Moving to heavier quarks, there are baryons containing charm quarks and bottom quarks, though these are much harder to produce and decay extremely quickly. Each of these baryons has a corresponding antibaryon made of 3 antiquarks, 1 of each anticolor. An antiproton contains 2 anti-up quarks and 1 anti-down quark. When a proton meets an antiproton, they can annihilate, converting all their mass into energy in the form of other particles. This annihilation is one of the most complete energy releases possible. converting nearly 100% of the rest mass into other forms of energy. Mesons are particles made of one quark and one antiquark, with the quark's colour cancelled by the antiquark's anticolor. The simplest mesons are pions. A positive pion contains an up quark and an anti-down quark. A negative pion contains a down quark and an anti-up quark. A neutral pion is a quantum mixture of up anti-up and down anti-down pairs. Pions are the lightest mesons, with masses of about 135 to 140 megaelectronvolts. They were first predicted by Hideki Yukawa in 1935 as the carriers of the nuclear force between protons and neutrons, and they were discovered in cosmic rays in 1947. Kaons are mesons, containing a strange quark or anti-strange quark. They're heavier than pions, about 494 megaelectronvolts. Kaons played a crucial role in the history of particle physics because they were among the first strange particles discovered. Particles that were produced easily in strong force interactions but decayed slowly, suggesting they carried a new quantum number that came to be called strangeness. There are also mesons, containing heavier quarks. The J/psi particle, whose discovery triggered the November Revolution, is made of a charm quark and an anti-charm quark. The upsilon particle is made of a bottom quark and an anti-bottom quark. These heavy quark mesons are sometimes called quarkonia because they resemble tiny atoms, with a heavy quark and antiquark orbiting each other. They've been incredibly useful for testing QCD because their heavy masses make certain calculations more tractable. In recent years, physicists have discovered even more exotic hadrons that challenge our simple picture of 3-quark baryons and quark-antiquark mesons. In 2003, the Bell experiment in Japan discovered a particle called the X3872 that didn't fit into any conventional category. It appeared to be made of 4 quarks, 2 quarks and 2 antiquarks, forming what's called a tetraquark. Since then, numerous other exotic hadrons have been discovered, including pentaquarks, particles apparently made of 4 quarks and 1 antiquark. The LHCb experiment at CERN has been particularly prolific in discovering these exotic states. These exotic hadrons are still color neutral. They still obey confinement. A tetraquark might be thought of as a pair of quarks bound to a pair of antiquarks, with the colors carefully arranged to cancel out. A pentaquark might be a baryon and a meson bound together, or 4 quarks and an antiquark in a more complex color-neutral arrangement. The rules of confinement allow any combination of quarks and antiquarks as long as the total color charge is neutral. 3 quarks, 1 of each color. A quark and antiquark with matching color and anticolor. 4 quarks and an antiquark arranged to be neutral. 2 quarks and 2 antiquarks arranged to be neutral. In principle, even larger combinations are possible. The universe doesn't care how many quarks are in your particle, as long as the total color adds up to white. Now, let's explore what happens when you push the universe to its absolute limits. What happens when confinement breaks down? Because there is one condition under which quarks can be freed from their hadron prisons. Not by pulling harder, not by adding more energy to a single flux tube, but by creating conditions so extreme that the concept of individual hadrons ceases to make sense. In the first microseconds after the Big Bang, the universe was unimaginably hot and dense. Temperatures exceeded several trillion degrees. At these temperatures, the average energy of particles was so high that they were constantly smashing into each other with enough force to create showers of quarks and antiquarks. The density of quarks was so high that flux tubes between individual quarks overlapped with flux tubes from other quarks. The gluon field was everywhere, filling all of space, saturating everything. Under these conditions, it was impossible to identify which quarks belonged to which hadrons. The quarks couldn't be assigned to specific protons or neutrons because the concept of a proton or neutron had no meaning. The quarks and gluons formed a continuous, undifferentiated soup, a plasma of color charges moving freely through a sea of gluon fields. This state of matter is called the quark-gluon plasma, and it's the only known state in which quarks are not confined inside individual hadrons. In a quark-gluon plasma, quarks can move freely over distances much larger than the size of a proton. They're still interacting through the strong force, they're still exchanging gluons, but they're not bound into specific hadrons. The flux tubes that normally confine them can't form properly because there are too many quarks and gluons everywhere, screening the color, charges, and preventing the flux tubes from establishing themselves. It's like trying to form ice crystals in water that's too hot. The individual bonds keep getting disrupted by the thermal energy of the surrounding medium. The quark-gluon plasma existed for only about 10 microseconds after the Big Bang. As the universe expanded and cooled, the temperature dropped below the critical threshold, roughly 2 trillion degrees Celsius, or about 150 to 160 mega electron volts in energy units. At that point, the quarks and gluons condensed into hadrons, a process called hadronization. Protons, neutrons, pions, and other particles formed from the cooling quark-gluon soup. And from that moment on, confinement took hold. Every quark was locked inside a hadron, and it has remained that way ever since. But here's what's remarkable. We've recreated the quark-gluon plasma on Earth, briefly in tiny volumes, under extraordinarily controlled conditions, but we've done it. The relativistic heavy ion collider, known as RHIC, at Brookhaven National Laboratory on Long Island, New York, began colliding gold nuclei at nearly the speed of light in the year 2000. Each gold nucleus contains 79 protons and 118 neutrons. When two gold nuclei collide head-on at these extreme energies, the hundreds of protons and neutrons are compressed into a volume smaller than a single nucleus and heated to temperatures exceeding 4 trillion degrees Celsius. For a fleeting instant, lasting about 10 to the negative 23 seconds, the quarks and gluons inside those protons and neutrons are liberated from their hadron prisons. They form a tiny droplet of quark-gluon plasma, a speck of the same primordial matter that filled the entire universe microseconds after the Big Bang. The results were surprising. Physicists had expected the quark-gluon plasma to behave like a gas, with quarks and gluons bouncing around independently like molecules in a hot vapor. Instead, it behaved like a nearly perfect liquid, the most perfect liquid ever observed in nature. It flowed with almost zero viscosity, meaning almost no internal friction. When the tiny droplet of plasma formed in these collisions, it expanded outward in a collective flow pattern, with all the quarks and gluons moving together in a coordinated wave rather than flying off individually. This collective behavior was the smoking gun for a true liquid state, not a gas. The ratio of the plasma's viscosity to its entropy density was remarkably close to a theoretical lower bound derived using string theory, of all things. This connection between the hottest densest matter ever created in a laboratory and abstract mathematical physics, was completely unexpected and has deep implications for our understanding of QCD and the strong force. The Large Hadron Collider at CERN has also produced quark-gluon plasma by colliding lead nuclei at even higher energies. The ALICE detector at the LHC, which stands for a Large Ion Collider Experiment, was specifically designed to study this state of matter. These experiments have confirmed and extended the findings from RHIC, revealing that the quark-gluon plasma is a complex, strongly interacting fluid with properties that continue to surprise and challenge physicists. What these experiments show is that confinement is not an absolute, eternal state of the universe. It's a property of matter at normal temperatures and densities. At sufficiently extreme conditions, confinement gives way to a different phase of matter, just as ice melts into water when you heat it. The transition between confined matter, where quarks live inside hadrons, and deconfined matter, where quarks roam freely in a quark-gluon plasma, is a genuine phase transition, similar in many ways to the phase transitions between solid, liquid, and gas that you're familiar with from everyday life. The study of this phase transition is one of the most active areas of research in nuclear physics today. Physicists want to understand the exact conditions under which confinement breaks down. They want to map out the phase diagram of QCD, a chart showing which phases of quark matter exist at different temperatures and densities. They want to know if there are other exotic phases of quark matter that might exist inside neutron stars, where the density is enormous but the temperature is relatively low. Some theories predict that at very high density and low temperature, quarks might form a state called a color superconductor, where quarks pair up in a way analogous to how electrons pair up in ordinary superconductors. This is speculative, but it's grounded in solid theoretical physics. Neutron stars are particularly interesting in this context. A neutron star is the collapsed remnant of a massive star that has exploded as a supernova. It's typically about 20 kilometers across but contains more mass than our sun. The density inside a neutron star is staggering. A teaspoon of neutron star material would weigh about 4 billion tons on Earth. At the surface, the matter is composed of neutrons, as the name implies. But as you go deeper, the density increases, and the neutrons are squeezed closer and closer together. At some point, the neutrons may be compressed so tightly that they overlap, and the individual quarks inside them start to interact with quarks from neighboring neutrons. Deep in the core of a neutron star, the density might be high enough for the neutrons to dissolve entirely, their quarks merging into a continuous quark matter phase. Whether this actually happens is one of the biggest open questions in nuclear astrophysics. Observations of neutron star mergers through gravitational waves, first detected in 2017 by LIGO and Virgo, are providing new data that may help answer this question. Now let's step back and think about what all of this means. What does confinement tell us about the nature of reality? Consider this. Every proton in your body has existed for roughly 13.8 billion years. Those protons formed when the quark-gluon plasma cooled and hadronized, roughly 10 microseconds after the Big Bang. Minutes later, during Big Bang nucleosynthesis, some of those protons fused with neutrons to form heavier nuclei like helium and lithium, but most survived as free protons, the hydrogen nuclei that still make up about 75% of all ordinary matter in the universe. The quarks inside those protons have been confined since the moment of hadronization, since about 10 microseconds after the Big Bang. Those quarks, the ones inside your atoms right now, have been imprisoned for the entire history of the universe. They were confined before the first stars formed, before the first galaxies assembled, before the Earth existed, before life began. They have been locked together since the universe was a microsecond-old infant, and they will remain locked together until the proton itself decays, if it ever does. Current experiments suggest the proton's lifetime is at least 10 to the 34 years. That's a 1 followed by 34 zeros. Far, far longer than the current age of the universe. Think about what the universe is made of at the most fundamental level. It's made of particles that cannot be alone. The building blocks of all visible matter. The quarks and gluons that constitute every proton, every neutron, every atom of every star and planet and living thing are particles defined by their relationships. A quark has no independent existence. It exists only in connection with other quarks and gluons. Its very identity, its color charge, is constantly changing through gluon exchange. The quarks inside a proton are not 3 fixed static objects sitting in defined positions. They're a dynamic, interconnected, constantly shifting web of interactions. The proton is not a collection of parts. It's a process, a pattern, a stable configuration of the quantum fields that pervade all of space. This challenges our deepest intuitions about what things are. We think of objects as being made of parts and parts as being made of smaller parts, all the way down to some fundamental level where you find the smallest, most basic building blocks. And in some sense, that picture is correct. Atoms are made of nuclei and electrons. Nuclei are made of protons and neutrons. Protons and neutrons are made of quarks. But at the quark level, the notion of an independent building block breaks down. Quarks aren't independent. They can't be separated from their context. They exist only as part of a larger whole. The building block metaphor, which worked so well for atoms and nuclei, fails at the deepest level. Reality at its most fundamental is not made of isolated things. It's made of relationships, connections, interactions. The quarks inside a proton don't have individual, separate existences that come together to form a proton. They exist because of the proton. The whole and the parts are inseparable. There's also something remarkable about the fact that nearly all of the mass of visible matter comes from the energy of the strong force rather than from the quarks themselves. It means that matter is, at its most fundamental level, made of energy. Not matter and energy as 2 separate things, but matter as a form of energy. The mass you feel when you lift a heavy object is the energy of gluon fields trapped inside protons and neutrons. The weight of the Earth, the mass of the Sun, the substance of every physical thing in the universe is overwhelmingly the energy of the strong force made manifest as mass through E equals mc squared. Matter isn't stuff. It's frozen energy, trapped energy, confined energy. The universe found a way to take the restless, dynamic energy of the strong force and lock it into stable configurations that persist for billions of years. Those configurations are protons and neutrons. And from protons and neutrons, the universe built atoms. And from atoms, it built everything. We've traveled a long way tonight. We start with the familiar world of matter and peeled it apart, layer by layer, until we reach the quarks. We learned that quarks come in 6 flavors and carry a strange property called color charge. We explored the strong nuclear force, the most powerful force in nature. carried by gluons that are themselves color-charged, creating a force that gets stronger with distance rather than weaker. We saw how this leads to flux tubes that store energy linearly with separation, making it impossible to isolate a quark because the universe would rather create new particles from pure energy than allow a single quark to exist alone. We learned that confinement is not a limitation of human technology, but a fundamental law of quantum chromodynamics, confirmed by decades of experiments and lattice QCD calculations. And we discovered that nearly all the mass of everything around us comes not from the quarks themselves, but from the energy of the force that confines them. These are some of the deepest truths that physics has uncovered about the nature of reality. They tell us that the universe is stranger, more interconnected, and more beautiful than our everyday intuition suggests. The solid ground beneath your feet is made of atoms that are mostly empty space, held together by electromagnetic forces, built from protons and neutrons whose mass is almost entirely the energy of gluon fields, binding quarks that have been confined since the universe was a microsecond old. Every object you've ever touched is a monument to confinement. Every ounce of weight you've ever felt is the mass equivalent of strong force energy. Every atom in your body is a tiny prison holding quarks that have never been and will never be free. And yet, despite being imprisoned, those quarks have built everything. They've built stars and planets. They've built oceans and mountains. They've built the cells of your body, the neurons in your brain, the thoughts you're thinking right now as you hear these words. Quarks can't be alone, but together, bound by the strongest force in the universe, they've constructed all of visible reality. Every sunrise, every thunderstorm, every heartbeat, every breath you take, all of it is quarks, confined and combined, doing what they've done since the beginning of time. There's a lesson in this, if you're inclined to look for one. The most fundamental building blocks of reality are particles that exist only in connection with others. Isolation at the deepest level is not just impractical, it's impossible. The universe is built on togetherness, on bonds that cannot be broken, on relationships so fundamental that the universe itself will create new matter rather than allow them to be severed. You are made of these particles. Every atom in your body contains quarks that have been bound together since the dawn of the cosmos, connected by a force so powerful that nothing in the entire history of the universe has broken it. You are, at the most fundamental level, a collection of relationships, of connections, of bonds that hold. That's what matter is. That's what you are. The next time you hold something in your hand, a book, a cup, the hand of someone you love, remember what you're really holding. You're holding quarks, trillions upon trillions of quarks, each one bound to its partners by gluon fields that have persisted since the first microseconds of the universe. Each one carrying a color charge that shifts and dances with every passing instant. Each one contributing its tiny share of binding energy to the mass you feel in your palm. Each one part of a story that began in the first moments of creation and will continue for eons beyond our imagining. Quarks can't be alone. And because they can't be alone, everything exists. The universe, in all its staggering complexity and beauty, is built by particles that must be together. That's not just physics. That's poetry written into the laws of nature. Thank you for joining me on this journey tonight. We've gone deeper into matter than most people ever go, past atoms, past nuclei, down to the quarks and gluons that make up everything. Remember, every time you touch something, Every time you feel the weight of an object in your hand, you're feeling the energy of confinement. The strongest force in the universe, holding the smallest particles together, building everything you see. Quarks can never be alone, and because of that, nothing else has to be either. Good night, and may you never look at matter the same way again.